Hello and welcome back to me answering questions from Robin Hartshorne's Algebraic Geometry. Today we will be answering question 1.9 from section 1. And so let's begin. This question asks us to show that the dimension of any irreducible component of the vanishing set of an ideal generated by R, which can be generated by R elements, has dimension at most n minus R. So let I be equal to f1 dot 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 fr within a and k. Now, what we would like to do is essentially do this step by step, but not by an inductive argument. What we will be doing is defining a bunch of algebraic sets. So, firstly, x naught is a to the n, a k to the n, and then xi is going to be the vanishing set of f1 through up to fi. F1 dot 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 fi. So obviously xi plus 1 is the vanishing set of f1 through to xi intersect the vanishing set of fi plus 1, and also xr equals v of I. And I will just say xi plus 1 equals xi intersecting with v of fi plus 1, just to make that very clear. So we want to let y of I be an irreducible component of our x to the I. Then it has to be contained precisely within, contained fully within another irreducible component of xi minus 1. It must be contained within some irreducible component of, well, let's call it yi minus 1 of xi minus 1. Now, what can we say about these two? So, either fi vanishes on all of I either fi vanishes on all of yi minus 1. I wish that I hadn't chosen such hard things to say aloud. Either fi vanishes on yi minus 1 identically, or it doesn't. Identically. If it does, then the two irreducible components are equal. So we're kind of done, the dimensions are the same. If it does, then yi minus 1 equals yi. Because otherwise it wouldn't, otherwise oh my god, yi is an irreducible component of xi equals xi minus 1 intersect v of fi. contained within yi minus 1 intersect v of fi. But an irreducible component is defined not to include any other irreducible sets. So then, well, this is equal to yi minus 1, but then this would then be an irreducible component of xi as well, which means that yi minus 1 equals yi, because they're defined not to be subsets of one another. So in this case, the dimensions are obviously the same. Now, if it doesn't, we further reduce this into two sub-cases, I guess the word is. Then either f is irreducible or it is reducible. Furthermore, yi minus 1 is a subset and not equal to the vanishing set of fi. Then we can use the result of question 1.8 and say that the dimension of yi is equal to, well, is an irreducible component of yi minus 1 intersect v of fi, which means that it's 1 minus the dimension of yi minus 1. In this case, dim yi minus 1 equals dim yi. Now, we should assume that f is reducible. Assume f is reducible. The polynomial ring over a field, I believe it only has to be a field, but definitely over an algebraically closed field, is a unique factorization domain, so we can factor this uniquely into irreducibles. Multiplied by a unit, but let's just pull those units in. Then there exist g1, comma, dot, 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 gd for degree, I will say, such that f is the product of them. I'm going to use big pi notation. I equals 1 to d of g1 dot 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 gd. Now, the vanishing set of two things multiplied by one another is either equal to or a subset of, it's equal to vs union vt. I believe, yes. Therefore, the vanishing set of fi is equal to the vanishing set of g1 union dot 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 union the vanishing set of gd. Also, this is finite because it just is. Essentially, division removes grading, and division removes degrees within a graded ring, and any polynomial ring has a standard grading with not quite gotten to the definition of a graded ring just yet. That's in section I.2, so I'm just using, I'm looking ahead, let's just say. But each of these are hyperplanes, so now not only are they hyperplanes, but well, hypersurfaces, not hyperplanes, I do apologize. But y of I is, well, y of I is an irreducible component of yi minus 1 intersect. So let's just call each of these h1 union dot 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 hd. Intersect, and I'm going to use the big notation, k equals 1 to d of hk. Uh, as yi is irreducible, it must be contained within some single intersection. So equals the union k equals 1 to d of yi minus 1 intersect hk. I will just write that. There is some index here, k, such that yi minus 1 is fully a subset of, sorry, yi is fully a subset of yi minus 1 intersect hk, because it's irreducible. Uh, so yi is fully a subset of yi minus 1 intersect hm for some m equals 1 through to d. Now I am actually going to prove this. Indeed, suppose not. Then, oh goodness. Choose m such that yi minus 1 intersect yi minus 1, sorry, yi on the original one. I hope I don't delete everything. Intersect hm is non-empty. I'll just keep that there. Now, yi is then a subset of the union from k equals 1 to d of yi minus 1 intersect hk, which is equal to the union of k equals 1 to d, and then k is not equal to m. Let's redo this. The union from k equals 1 to d, and then k is not equal to m, of yi minus 1 intersect hk union yi minus 1 intersect hm. In fact, I think that right now I am taking the executive decision to pull out the yi minus 1. yi minus 1 union from k equals 1 to d, k is not equal to m, hi union hm. So then, yi is equal to yi intersect Whoops, I made a mistake here. yi minus 1 intersect that. yi minus 1 intersect union from k equals 1 to d, k is not equal to m, hi union hm. And yi is a subset of yi minus 1 by supposition over here. It's an irreducible component contained within this, so this is just equal to yi equals yi intersect union k equals 1 to d, k is not m, hi union hm, which is equal to, drumroll please, union k equals 1 to d, k is not m, yi intersect hi union yi intersect hm. Now, we have finally gotten to the point where we can say hm is not contained within, hm does not contain yi by presupposition, and it is not empty by presupposition. Therefore, it is a proper closed subset of yi. Now, this bit is also non-empty because it equals to yi, and it also, I should pull the yi out of that. Let me say yi equals yi intersect union k equals 1, k is not m, hi union yi intersect hm. Now, yi is an irreducible set. Therefore, it cannot be expressed as the union of two proper closed subsets of it with the subspace topology endowed with it. But this is precisely what we've done. This is a proper closed subset of y. Therefore, this is a proper closed subset of y because, well, if this were empty, then this couldn't, this would hm would have to contain yi, but that was supposed not to be the case. And if hm is not empty, then I'm just thinking that this could still contain, or I guess perhaps not. I was thinking the bit on the left still could be not a proper subset. However, if we just pulled out every single k and just wrote yi equals yi intersect h1, h1 union yi intersect h2 union dot 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 union yi intersect hd. All of these are proper closed subsets, and all of these are non-empty. Well, discard the ones which are non-empty, then you can kind of smush them together because they're finite into two proper closed subsets of yi within the subspace topology. Therefore, this violates the irreducibility of y. Thus, uh, thus, yi is fully contained within yi minus 1 intersect hm for some m. Okay. Therefore, yi is an irreducible, is an irreducible component of yi minus 1 intersect some hypersurface. Therefore, the dimension of yi minus 1 is equal to the dimension of yi. Now, we see the dimension of uh, all irreducible is an irreducible component of x naught. Well, x naught is equal to a to the nk is equal to n. Now, if we do the exact same thing one step below to x1, dim y such that y is an irreducible component of x1 is either n or n minus 1. And then I think you can see where this goes from here. It's either n if f1 vanishes identically everywhere, i.e. f1 is equal to 0 for some reason, which, that's actually not the case. However, the next one is would either be n minus 1 or n minus 2. And then dim y such that y is an irreducible component of x r minus 1 is equal to, let me just properly do this because I like writing nice curly brackets. That's better. N minus 1, n minus 2, dot dot dot, n minus r minus 1, dim y, such that y is an irreducible component of xr is, I am sorry, n minus 1, dot dot dot, n minus r plus 1, n minus r. But x to the r is equal to the vanishing set of our original ideal. Therefore, the dimension of, I should say, I should actually show that this fulfills the requirements of question 1.8. So we want to show that yi minus 1 is not a subset of h to the m. If it was, then gm would vanish identically on yi minus 1. And therefore hmm, hmm, well, therefore f equals g1 dot 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 gm vanishes identically on yi minus 1. Therefore, this is true. Therefore, we can use question 1.8. Also, the reason why I removed n from here is you can't add 0 to an... You can add 0 to an ideal, but what is there to generate then? Especially, well, yeah, no, sorry. Reduced and has no nilpotent elements, but can it have any 0 divisors? That's something for me to think of. Anyway, the dimension of an integral domain is the... Okay, therefore, the dimension of any irreducible component of Vi is, well, less than or equal to n minus 1 or greater than or equal to n minus r. Greater than or equal to n minus r. Therefore, we are done. And I will think about my question. Yeah. Yes. Yes. I'm pretty sure that k adjoint x1 dot 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 xn is an integral domain, which means that 0, the ideal generated by 0 is just equal to 0, because if not, then... Right. Anyway, I will see you. Thanks for watching. What? I don't even know what I tried to write there. Thanks for watching. Smiley face. Okay, goodbye.